Okay, this is the slide from where we have to start. We finished with this slide yesterday, and now we have to see the backtracking for this Sudoku puzzle. Come here. Why you all are there too far from this table? So the topic is backtracking, and now the problem is Sudoku solver or Sudoku problem, you can say. For the previous problem, the initial state was just empty chessboard, but here the initialization is we will begin the problem with the partially filled Sudoku grid. So it would, now that Sudoku grid that we have, it would not be totally empty. We will start with some partially and randomly filled numbers. For example, you can see here, it is a 2 cross 2 grid, which means this is a 2 cross 2 grid, 2 rows, 2 columns. And this is again a 2 cross 2. So this is the second quadrant, you can say. Then you have here, and similarly, you have this fourth quadrant, also the grid, fourth grid, 1, 2, 3, 4 grid, and each grid is 2 by 2 here. So our initialization would be what? Partially filled with some values, partially filled, all. And then the step number 2 would be find an empty cell. So suppose that this is the empty cell, which has the color light yellow. Suppose that it was initially empty. Suppose that it was initially empty. So we selected that. And then the step number 3, then we tried possible values. What are the possible values? For example, each row contains 4 cells, each column contains 4 cells, and each quadrant contains 4 cells. If I will remove it, each quadrant contains 4 cells. So we now, if this was initially, now this, if it was empty, we are assuming that it was empty, and then we will try any value from 1 to 4 for this, and initially we are trying with 1. Initially your algorithm will try with 1, 2, 3, 4, one by one, huh? If you have imagine a tree like that, then after that you have 1, 2, 3, and 4. You will try 1, 2, 3, and 4, something like that. But here we cannot draw the huge tree for this. So that's why anyhow we are assuming that we have 1 here. Not huge, huge is not a proper word, but I don't want to draw the tree here because we have already taken an idea from this example. So when you are going, so now this step number 3 is finished. We have to try any number or 1 by 1 number from 1 to 4. And then step number 4 is we have to check the constraints. Constraints mean conditions. What conditions we have to check? We have to verify something, that the number that we have assigned here is following the Sudoku rules. And what are the rules here for this problem? The rule is that you don't have that number already existing in the column, in the row, or within that grid. Oh, 3 conditions, huh? Are within that grid. So here, if you will give 1, it is already in the grid and also it is in the column. Then what? You have to check. You have to replace this number with the 2. Now you have to check 2. And then here we are checking 2. And in the column and in the row, 2 is okay. And within the quadrant, It is, and within the quadrant, it is also okay. So now all the constraints are okay. This step number 4 is finished. And then you can select some other empty cell, and then you can try the values from 1 to 4 again. So here, for example, we are checking this with 3. We have inserted 3 here. And similarly, here I have mentioned dot, 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 which means from this point to this, there are many steps involved in it, okay? I cannot draw all the pictures. So then here, now we are going to put something here. If I will put 4 here, then 4 is already there, so not okay. If I will introduce, I cannot introduce, for example, 1 is already there, 2 is already there, 3 is already there, 4 is already there. So all values are failing. All values are failing. Then what? We have to go step, we have to go into the previous step. This is called backtracking. This is called backtrack. So here, when you assign any number in this cell, then it is violating the constraints. And if it is violating the constraint, we have to go back to the previous cell. And then we have to try some next value for that. So we have to go back here. And then we have to try 4. But again, 4 is there. 4 is not valid. So again, this is also failing. And if it is also failing, then we have to go back on this. And we have to check maybe 3. 3 is already there. And maybe we have to check 4. Okay, 4 is with this row, with this column, and within the quadrant, it's okay. And when you are done with the 4, then you are coming here. 1, 1 is there. 2, 2 is there. 3, okay, 3 is okay. And then here you are checking for this 1, not 2, okay. So then all the values here in this quadrant are okay. So those steps are mentioned here. If the valid number is found, the number that you have placing here in the cell, if it is valid, if it is valid, then you have to proceed to the next cell. And this is how I am proceeding. First, then second, and then third, and then fourth, and similarly like that. And step number 7, you have to move to the next empty cell, and you have to repeat the step 2 to 5. Step 2 to 5. You have to repeat this recursively for finding the solution for this problem. And when all empty cells are filled with numbers, you have your solution. Like here. Like here, yes.
It's not clear how the backtrack here is wrong. You said if the 3.
It will be clear, okay? In this picture, it will be clear. Here, we cannot draw the whole picture. So that's why. That was the discussion here, okay? That was the discussion here by skipping many steps here. Now it will be, look over here. So now we have this state. We cannot draw the all things. So now you only have to think about these green cells. What are the values for that? And the rule here is not all the 3 conditions. There were normally for Sudoku, you have 3 conditions in the row, in the column, and within the grid. Here we are not looking into within the grid. Here you don't have that 2 by 2 grid, okay? Here you don't have that 2 by 2 grid. Here you have 4 by 4, you can say, okay? So here you only have to check 2 conditions, row and columns. And then, okay, so we are starting with this state. And then the algorithm is working. It is putting 1 in here, selecting empty cell, putting 1 in it, then 2 in it, then 3 in it, and then 4 in it, 4 values. And then this is not okay. Okay. Crossed, so which means we cannot go further. 1 is not allowed. 2 is also not allowed. 3 is also not allowed due to this reason, which And 4 is okay. Okay. If 4 is okay, we are going next. We are selecting another cell. And here in the next step, 1, 2, 3. So this one and this one, this two and this two, so they are not allowed. And then 3 in this row and in this row and column, it's okay. So that's why we are moving next and we are checking this one. And here we are with the 1, putting 1, okay. This column, this row, everything is fine. So this is finished. Now, suppose if this value is, you don't have a value here, okay, suppose I'm just saying, then you have to go back to this previous step, and then you have to go back. Here you have given this value, which is 1 is not okay. 2, 1, 2, 3, 4. If all are false, maybe I can select some other scenario here, because this is not right, because then you don't have further options, huh? You don't have further branches of the tree, huh? So, for example, here, or again, maybe I will, yeah, take this maybe. And suppose that the number that you are putting here, 1, 2, 4, 3, all 4 values, if all are not giving you the proper result, then what you will do? You will go back to the previous step. You will go back, and then what is the previous value here? Here, all the values are not giving you the solution. Then what is the option? Actually, you have to, if this cell is not giving me the solution here by putting any value from 1 to 4, you have to go back to the previous step. And previous value is this, the green one. You have to change the value this. You have to change this value. If you have a value 4 here, you can check. If suppose it is 3 here, then you can check 4. You can check with some other numbers, so that you will have further options which will not have this failure condition. This is what I want to explain here. And if you understood this algorithm, you don't need that. Even this example is enough when we study this. But I am putting more, two or three examples. That is not a complex algorithm. The simple strategy, wherever you have failure or wherever your algorithm is stuck, you have to go back to the previous step. And then you have to change the options for that previous step. And then you have to come again to that step, and then you will not stuck. This is the simple strategy, nothing else. Here, maybe that confusion is solved here, but it is red here. Maybe I will make the previous slide red, and this, I will remove the red color from here. This red color means read it by yourself, okay? For example, here we are checking 1 here. And in this row and in this column, it's okay, huh? And then we are checking this. In the next column, we are checking this. This 1 is not allowed here. So that's why next we are putting 2 here. In this row and in this column, this 2 is okay. Yes, it is okay. The green color means okay. And then we are considering this circle 1. 1 in this is not okay. So we are changing this to 2. Due to this, it is not okay. We are changing it to 3. So 3 is not okay. 1, 2, 3, we checked all. And it is not okay. Then we have to backtrack. We have to backtrack where? In this. And here one option is left. So that's why now this back. So now we will change it to 3, which you are seeing here. This is that backtracking. We will go back. We will change it to 3, which we are changing here. And then you are coming again to this current. First, you will check one, it is not okay due to this one. And then you will check two in this row and in this column. Now it's okay. Now no issue. Now that problem is solved. And then you are checking this, and that, which is mentioned here. Now, again, backtracking with maze puzzle. Here, this is the starting. This is the destination. So the start is begin the maze with the starting point and explore paths. You have to path up, down, left, right. These are the four operations that you have checked in your previous lab exercises. Okay. So you have to check here and then mark visited. You can read it by yourself. And then finally you will reach here at destination. So you can solve this maze puzzle also by using that backtracking, where it can happen something like that. When your path will come in this direction, it will go in that. And when it will hit with the boundary, it will be failure. Huh? Then it will backtrack. Then from this point, it will backtrack here. And then it will check, okay, in the right direction, option is available. And then it will select the path in this way and finally reach that. So I cannot explain each and everything. Okay, I have even this example was the most simple example and most easiest example to understand backtracking. Anyhow, this has further clarify your concept with respect to Sudoku puzzle. And now moving toward this variable and value ordering. We have understood previously on this slide that we can improve the backtracking by doing something with this function, select unassigned variable. We can change the order of the variable selection, and then we will have improvement in backtracking. Similarly, we can change the values of the domain, which is red, green, blue for that example, and we can improve the backtracking. Now, again, the same thing. Can we do something with the variables and the values ordering? Can we do something with the order of the variables that we would select? Or can we do something with the values that we will select? And the first technique is MRV. Yes, we can. The first technique is MRV, minimum remaining values. The definition is written here. We will choose the variables, the variable that will have few legal values left. Okay. So this is one variable, this is another variable, this is another variable, this is another variable. It has names in that problem. Huh? So those names has, I'm calling them the variables. So now which variable I have to select for color? For example, it is done, it is done. Now when these two are done, now which variable I have to select? If I have to select this or this. When you have these options, then one option is MRV. You have to choose that variable which will have few legal values remaining or left. For example, after giving color to these two, this one and this one, after giving color to these two, now I should have to color this or that. This, I can give it has red and blue option, huh? And this has how many options? Only one option, blue. So this variable has few options left as compared to this variable. As compared to this variable. So this has two options and this has one option. So that's why I'm using the word few. So you have to select that variable which will have few options left as compared to other. Or you can say you have to select that variable which will have less number of options available as compared to other variable, or which is going to fail first. So if you are not going to assign this blue here, and if you assign blue here, then it will be, it will become failure. Huh? So you have to select that variable which is going to fail first. And in this case, you have to select SA here, and you have to assign that color blue here. And when you will select blue here, the all other colors, these two, you will have the red here, and these two, you will have the remaining one, these two, and you will have the remaining one. And if you do that, actually for others, you will have one advantage, that for others, you have only one options left. And then you will do that quickly. So this is called MRV. And in this MRV, you have to select that variable which is going to fail first, or which has the less options left as compared to the other variables. And this thing which I discussed here is mentioned here. And if you will go with the chronological ordering means the ordering which is given in the set. If you will select according to that order, first this, then second, then third, then fourth, this is not efficient. Okay, this is not efficient. This is called chronological ordering, and this is not efficient. This is not good option. Then what? This MRV is a good option, but for the initial state, it is not a good option. Initially, how many options left? Each have three options, huh? Initially, each have three options. Initially, each have three options, then MRV cannot decide here. MRV normally decides in between, after the initialization. And then maybe then there is another heuristic which is called degree heuristic, which can help you maybe in initialization. At initial step, it will help you which variable you have to select. Huh? What is degree selection? You have to count the number of degree for each variable. That number of degree here is what? 2 neighbors. The number of degree of this thing is what? 3. The number of degree this 5. Similarly 3. Maybe 1, 2, 3. And here 1 and 2. So you have some variables with degrees, and then you have to select that variable which has the highest degree. Now this degree heuristic is helping you for the initialization, for the initial step, which this MRV was not helping you, which this MRV was not helping you. So here SA has the 5. So okay, you have selected that. You have given this some color to this SA. And then after that, this has 3, this has 3 maybe, and this has 3, huh? And then you can go by clockwise, or you can select any. If all have equal, you can select any among those equal. And here in this example, we are selecting this, and then maybe this. And then this has the 2, this has also the 2, and then you can select if you want to go clockwise, or you can go in any choice. So when you apply, and this example is discussed here in this point, when you apply the degree heuristics, then you can solve these all other options actually without any issue, without any false step. This is mentioned here. So all that discussion is we already did when we were saying this thing. Okay, the least constraining value now. This is the third technique in variable and value ordering. And here, the heuristic will try to leave the maximum flexibility for the variables which are coming next. For example, when this is done, when these two colors are already assigned, now you have, if you will assign this, you have what options? If you will give this red here, so then what option is left for SA? One value. And if you will assign blue color here, zero option left. It will look similar to your MRV, your first measure. It will look like similar, but with a different angle. With a different angle. It will select that variable which will left maximum options for the others. Okay. For the others. So here, this least constraining value, it will assign now, after this, it will assign red color to this and not blue. And it will leave the option for the other variable here. This is the purpose, huh? This is the purpose of this heuristic. Again, what is least constraining value? This is a heuristic. It will assign some value to the variable. How? It will look over all the variables which are coming next. For example, after assigning this and this, these variables are coming next in neighborhood. Now we can assign color here or here. And here we are thinking here that if we will assign color blue here, then this we are not leaving any options for this other variable SA. But if we will assign this here the color red, then we are leaving option for the SA. So based on this, we will give this region the color red, so that the option for the SA will remain and it will not die. So we are providing now life to other variables in this constraint. These things are discussed here. Now, inference. I talked about inference when I was discussing something on this slide. And I told you that inference is something, your algorithm is at a current point, but inference function will look 3 or 4 layers ahead than this current point, than this current point. So now we are going to see something like that. And why we are going to see 1 or 2, 3 layers ahead than the current point? Because we want to detect failure if there is a failure in the next steps from our current step. So the first option that we have is the forward checking in inference. In inference, the first option we have is forward checking. From its name, it is clear that we will check something in forward direction. In forward direction. This is the definition. If we have a variable x, and if we will assign some value to x, if we will assign, so suppose that we have assigned some value to variable x, value is assigned, then we have to see what? Then we have to see its related variable y, its connect, the other variables which are connected with that variable x, the other variables which are connected with that variable x, we have to see that. And if the values are unassigned to that variable y, which is connected with x, by constraint, maybe neighborhood, We are taking that example, the same Australian example, and here in which we have variables which are connected with each other. So if we have a variable x and that variable x is assigned with some value, then we have to see the variables y which are connected with this variable x, and we have to remove the values which are inconsistent with the x, which are similar with the x, you can say. I am using the word similar because here we have the picture. So that's why similar is appropriate for it, otherwise inconsistent. Again, in forward checking, you have to do what? You have to see the variable x. You have to assign some value to x. When you will assign, for example, here, you will assign some value red, green, blue to this variable. And suppose it is, I am, just a minute. Suppose I am calling it x. And when you assign some value to this variable, now you have to check the variables y, which are connected with that. This is connected. This is connected. This is connected. So this is y, huh? This is y. This is y. This is y. So if you assign one value to this x variable, any red, green, blue, then you have to remove that red, green, blue from the y, because you have assigned that color to that x. This is called forward checking. This is called forward checking. For example, now let's have a, so here some extra information is written that this forward checking normally does the arc consistency. Arc consistency is also a technique similar to forward checking, which is, we will discuss it here, okay? We will discuss it here. But now coming back. So forward checking is what? It normally does the arc consistency. And if you already have done arc consistency for your problem, then there is no need to do the forward checking, okay? They are almost similar. Let's see that how it is. For example, here now we have given red color to this war. This is the war, the variable war. We have given red color, huh? And what are connected? This war anti is connected, SA is connected. And we are removing this red color from anti here, we removed. And also from SA we removed, according to the definition. Now, here, when we assigned this war anti, this is maybe Q, huh? Queensland or something. When we assigned this Q, the green, as you are seeing here, this is X. And what are connected? This is connected. Anti, green finished. This one previously the green was here, but now it is finished. And SA, okay, SA green finished. And then this might be NSW and this green finished. Moving next. Similarly, when we assigned this color blue, and you can see the effect of this blue here. This is Victoria, color blue. What are neighbors? SA and I don't know, maybe this is Queensland, NSW, huh? So from NSW, this is blue is removed, and SA blue is removed. It is removed, okay? And according to the definition, you are simply removing. But this is now the problem, huh? No any color left for this essay. No any color left for this essay. So now, what is the drawback here? Forward checking, here we are just one step. If we assign some color, we are removing the colors from the Y. Nothing else, huh? Nothing else. So consider this example. When war is red, this is war, and Q is green, and this is green. So then anti and SA both are blue. Anti and SA. Look at here. Anti and SA. When we assign this color and this color to these regions, then we have what? Then anti and SA, what we have here? Blue. So this is also a inconsistency. This is also a inconsistency because anti and SA are neighbors and they cannot, and they have only one color remaining. So on this step, it was an inconsistency. On this step, it was an inconsistency. But this forward checking has not detected it until we assign this color to SA, and then it will remove from here. And then you have this situation, nothing left, huh? Nothing left. So forward checking, okay, it is good, but it is not able to detect all different kinds of inconsistencies. We can say it is okay. For example, at the current situation, it is explaining the current situation only. It is explaining only the current situation only. It is not looking 3 or 4 steps ahead than the current situation. Than the current situation. It is not looking ahead actually. But we have seen what is forward checking. And now we will move on to our consistency that will check 3 or 4 steps ahead than the current step. And this is the definition here. If we have x implies y, x is a variable, y is also a variable. We can call it that whatever the assignment you will do with these variables, that will be consistent if and only if for every value x of x, there is some allowed y. For variable x, you will do the same things like forward checking again, but in a different way. But in a different way. And then you will say finally that this x implies y, that assignment would be consistent if and only if for every value x of x, these x can be red, green, blue, the small x, huh? X of x, there is some value allowed for y. There is some value left for y, you can say. For example, here you have this situation. This is red, this is green. And when you have done that, y is equal to, just put this picture in your mind so that everything is okay. Y is red. When y is red, red is gone from this anti and SA also. Anti, no red, SA, no red. And then when you make this Q green, this green is gone from anti, SA, and NSW. Anti, no green, SA, no green, NSW, no green. Huh? So now Now, if you are going to say that this essay is left with only one blue color, and if you are going to say we are going to give blue to essay, for every value x of x, there is some allowed in y. So now this value, one value is left for essay or maybe NT. We will check it. But first we are checking this essay. So now we are going to give this value to this essay. And if we will give this color to essay, we have to check that its neighbors, essay. What are the neighbors? NSW. And here we are checking this and then we will remove it, which you are seeing here. Now it is removed and then now this essay is clear. Huh? You can assign this blue to essay. So this is one step, but it is not finished yet. This is our consistency. It is not finished yet. When you are when something is removed from NSW, now you have to check. When this blue will be removed from here, then you have to check NSW. You else this blue is removed, then it has only one color, which is red, which is now its color. Huh? Then you have to remove this red from its next neighbors. Huh? So if this is NSW, NSW is this. We already done with the essay. NSW is the neighbor of this Victoria. And then from the Victoria, you are checking that this red is available. And then you are first, the arrow is like that. And then the arrow is in the backward direction that you are checking and removing. Process is not finished yet. Here you have two. Okay, then you are stopping, huh? Because you have two options available there. You started from here again. Why? How are consistencies different from forward checking? Here on essay, you have only one color left, which means now this blue is the color of this essay. And if it is, you have to remove this blue from its neighbors. What are its neighbors? These are neighbors, huh? But you can do it one by one, okay? You cannot remove all together, huh? So that's why we are first checking this NSW. You are checking that this blue is available there. Okay, then remove it, which you are seeing here. You have removed. And when you removed, this effect is now, look at this NSW. This new situation emerged. Now, step one, now you are checking step two, huh? In the same sequence. Our consistency is not finished yet. When our consistency was doing this consistency means making the things legal, huh? So now only one, again, this NSW is left with one color. So now it means NSW has now the red color. If it is the red color, you have to check the Y. You have to check the connected variable of, now NSW is what? This one. Essay is already done. And this is the neighbor, which is Victoria. So you have to check this red in the Victoria, which you are seeing here. I will check here in the V. Red is available. And then that one red is only for the NSW. So you have to remove this red from the Victoria. And now you are going and coming back after removing it. Now this Victoria has two colors. Now you have to stop. And then you have to check it again for this, maybe. Or the previous step, when you were checking this essay with I think when you were checking this essay with, I can remove this drawing so that you can understand. When you were checking this essay here, then this new image come and then you will come back again SA with NT, because NT was the neighbor. This neighbor is now finished. Neighbor of SA, this is finished, but this is something remaining that you have to check. So I mentioned this, if X loses a value, neighbors of X need to be rechecked. Okay. Rechecked. So if this NSW has lost the value, so this neighbors of this NSW you have to recheck. Now again, so if NT is equal to, now if you are saying NT is, this has the single value NT, huh? If you are going to assign this blue to this NT, where it is, who are the neighbor? SA is the neighbor. You are going to check it. SA is available there. Remove it, and then you are coming back. And if you are removing it, then R consistency will show you that there is no any color left for the SA. No any color left for the SA. And here you don't have, you are calculating all these things in one step. In one step. This is called R consistency. And this R consistency can detect failure earlier than the forward checking, because forward checking is checking only at the next step, not next to next to next, huh? In a sequence. And this R consistency checks next to next steps in a sequence until you have a failure or the values will be consistent. What is the finishing time of this lecture? 45? 45. Intelligent backtracking, the last topic of this CU, I suppose. Yes. So this is again the backtracking, but intelligent. But first here we are presenting a scenario, and then we will identify from that scenario that what is intelligent backtracking. Suppose that we have this set Q, NSW, V, T, SA, whatever it is. Suppose we have to select the variable according to this order which is given in this set. This is when you are selecting the variables according to the order given in the set. This is called chronological order. And if something, and if something will happen, I don't know what is happening with me. So in this set, when you are assigning colors to this, to the variables, if something will happen, which means if failure will happen at some point, suppose war, then you have to go back. Then you have to go back like a depth first approach, and the one by one. If by going back one step solves your problem, it's okay. If not, then you will go back further one step. If it is solving your problem, it's okay. Otherwise, you will go back further one step behind for solving your problem. So this is called, when you are going backward in this order, that is called chronological backtracking, because you are following the order which is given in the set. So that's why it is called chronological backtracking. With this option, with this chronological option, suppose we have this situation. You have assigned the color Q red, and you have assigned the NSW the green, and then after V you assigned the blue, and then T you assigned red. And now the question is what you are going to assign to this SA. Now this is the question. So this red, green, blue is already assigned. 3 colors are already assigned. No any color is left for SA. So now failure occurred. So you will do what? You will do backtracking. And failure occurred here. And if you will do backtracking, you will go here at T. And T is separated from it. Changing any color will not give you the solution. Huh? It will not give you the solution. So so chronological ordering is not helping us here in finding the solution. Then what is the uh, best way to do something? So is there we have to jump over this Tasmania. We have to jump over this Tasmania. And then we have to search some value maybe for V or NSW or Q. Maybe this V, NSW or Q, maybe they all are, I don't know. Maybe I will get the value solution from V, maybe NSW, maybe Q. So when you are jumping over Tasmania and identifying some set like here, Q red, NSW green, Q red, NSW green, and V is equal to blue. These are the values which you already assigned to these. So when you are jumping over Tasmania and going into this set for finding the solution for SA, this is called conflict set. This is called conflict set. And identifying this conflict set and going into it and then changing options, changing values there, and then coming back again and finding some solution. This is called conflict directed backtracking because you move toward the conflict set. So that's why the name is conflict directed backtracking. And here then you can go back into V and you can change the color to red. And then you have option now for the essay. So jumping over the options and going back to proper option is called the intelligent backtracking, nothing else. And this is the end of this CLO. And